So today we're going to conclude the 1.2 notes. This will be 1.2b. We left off here this example because completing the square for this question was not going to be pretty. Well, we're going to do it because we've been told to. So let's go ahead and complete the square and get it into vertex form, and then we will sketch the graph from there. Before I do, because I know I'm sketching the graph, I might as well steal some free information from the equation. And that free information is going to be right, come on now, that free information is going to be right there. When a quadratic is written in standard form, that number that's added or subtracted at the end, that will always intercept. So we'll use that knowledge to help us graph this thing. So that little +1 right there is your y-intercept. Let's start completing the square. Remember, you can't complete the square if there's a number in front of your x squared. So what you have to do is you have to pull that number, that 3, from the first two terms as if it is a GCF. No, it's not. But we're just going to say, oh, well, if we divide by 3, here's what we get. And remember, you're only taking it from the first two terms. And here's the +1. I didn't take it away from the +1. We're trying to complete the square with the inside of those parentheses, so we have to find this value right there that would complete the square. But while I'm here, remember, I'm not allowed to just alter this equation. I can't just put a +c here without doing something else about it. Because this is all going to happen on one side, the only thing I'm actually allowed to add is 0. So I need to make sure that I cancel this +c that I just wrote at the exact same time. But I can't just write -c on the outside because of this 3. You see, if you were to distribute that 3, you would actually have a +3c. You'd have a +3c, which is why I'm going to write -3c right there. Now I've essentially done nothing. If you distributed the 3's, you'd have a +3c and a -3c, and those cancel out to give you nothing, which means you have not altered your equation. Finding that c value is not going to be pretty, though. So b over 2, well, normally that would be easy, right? But b is already a fraction. So I'm asking you to cut a fraction in half. When you cut a fraction in half, basically what that does is it just doubles the bottom. Because it's the same thing as multiplying by 1/2. Or if you're lucky, instead of doubling the bottom, you could just divide the top by 2. Either way, it doesn't matter. I'm gonna do it like this: 1/2 times the -4/3. When you reduce your fraction, you will get -2/3. That's from reducing the fraction, because it would have been -4/6, which would have reduced to -2/3. You know, if I could say it, I can write it. I'll just go ahead and. There. Okay. Now your c term is found by squaring that result. Now that result's important, that -2/3, because it is going to go right there. So let's square it. Which has a net result of squaring the top and squaring the bottom. Gives you +4/9. Ew. That is not fun. Yeah, no, it's not always pleasant, to be real with you. And minus this 3 times 4/9. Yeah, no, it's not pretty, but it works. So that set of parentheses is now a perfect square trinomial. We have the 3 on the front. We have a set of parentheses squared, x, and then that b term, which was -2/3. Like that. Now on the far right, because I'm trying not to take up too much vertical space, on that far right, what I'm working with is, so I'm taking this stuff here, and I'm just going to do it over here. It gives me 1 minus 12/9. Well, 1 is 9/9, right? So 9/9 minus 12/9 gives me negative 3 over 9, which reduces to negative 1/3. Negative 1/3. There, it's in vertex form, but man, it's not pretty. But you got to do what you got to do, right? Yes, sir. Miles. Oh, yeah. They want us to sketch this graph. We know where the vertex is, which means we also know the axis of symmetry. We also know that this thing points up because the 3 on the front is positive. Remember, positive people smile. And I just realized I don't know what camera my gentlemen are looking at, so let's make it so that they can see me better. There we go. So we know vertex, which means we know axis of symmetry, we know y-intercept, we know it points up. That's enough. Do I have space? Of course not. All right, well, we're just going to squeeze this graph somewhere, aren't we? Picture not drawn to scale because, yikes, it's small. Our vertex, go ahead and write it down. So what makes the inside equal 0, which is going to be positive 2/3, comma, the number to the far right, which is negative 1/3. And that should be more than enough space right there. Sorry, the picture is going to be so small. I wrote too large. So let's see. If this is a 1, then this is a 1/3, this is a 2/3. And if this is a negative 1, this is a negative 1/3, negative 2/3. Trying to keep my picture to somewhat scale, and there's positive 1. Our vertex was at 2/3, comma, negative 1/3. Eek, this thing squeaked. And the y-intercept was positive 1, which was 2/3 to the left. So if you did 2 more tiny tick marks to right there, was that 1 1/3? Then you would just reflect that y-intercept over the axis of symmetry. I didn't draw it, but if you needed to, here's your axis of symmetry. So quick sketch. There we go. Ta-da! So to be honest with you, this one wouldn't have been easy to graph, even in standard form, would it? It wouldn't have been pretty. So yeah, you will run across 1 or 2 of those in the homework. Good news is, I have never seen an IB question that made you complete the square with ugly fractions. That doesn't mean they never will. This means I've never seen one yet. Well, if I've never seen one yet and all of your tests are made out of former questions, then that means you won't have any with fractions on your tests. Because I think the reason why is because this mathematics class is not about fractions. This mathematics class is about having a deep understanding of mathematics itself. So why would they try to trip you up with stupid fractions if you understand the math? You know what I mean? I'd say that's probably the logic behind it. So what about graphing a quadratic in standard form? Now, I'm aware all this is still review, but what about graphing a quadratic in standard generic form, ax squared plus bx plus c? The axis of symmetry, x equals negative b over 2a. We've been trying to beat that formula into your brains since Algebra 1. Hopefully you have that one mastered. X equals negative b over 2a. If you want to know the y value, whatever number you get from negative b over 2a, you plug it back in. So the one we were just doing, if we had found the axis of symmetry happens to be at positive 2/3, you would have had to have plugged in 2/3 into standard form and played a fraction game. And I don't think it would have been any easier. Luca, you had a question for me. Interesting. I think. I'm not sure. I have no clue. Am I actually recording now? Yes. Okay, good. The little red dot came on. All right, so where were we? Oh, yeah. The y-intercept is that c value at the end. It's the constant. Whatever constant is written at the end of y equals ax squared plus bx plus c, that c value is always your y-intercept. Once you have it, you can always just plot its reflection over the axis of symmetry. And you can find the intercepts by factoring or the quadratic formula if it's pretty enough. And then you just graph it. I mean, it's pretty simple stuff. We've done this before. It's Algebra 1. So we've been asked to find all kinds of crap about this, and at the very end, hence, sketch the graph. And in IB, the word hence means, that means you have to use all the stuff you just found. That's what hence means. So oftentimes on a test, you'll see a part A, and then it'll say find something, and then part B will say hence do something else. That means the result you just got is necessary that you use it in the next part of the question. So let's find the axis of symmetry. X equals negative b over 2a. So that's negative 8 over 2 times 2. So our axis of symmetry is at x equals negative 2. That's the x value of our vertex. Well, part B says find the vertex. So if you want to know the y value, you just plug it in. So y equals 2. Here's us plugging in negative 2. So what is that? What? 8 minus 26? Ooh. Negative 18, I think. You guys are welcome to check my math. 8 minus 26? Yeah, that's negative 18. So our vertex is at negative 2 comma negative 18. Oh, that was, all right, so that was part B. Part C says to find the axes intercepts. Part C. Well, the y-intercept is free. It's free money. It's at negative 10 because it's right here. So we know a y-intercept at 0 comma negative 10. But in order to find the x-intercepts, we're going to want to either factor or use a quadratic formula. I'm pretty sure there's factors. So we'll pull out the GCF of 2 because we see that all three of those terms are even. X squared plus 4x minus 5. And the two numbers that multiply to be negative 5 that add to be 4, or 5 and negative 1. Yeah, just from it, I got the negative 18 just by, I plugged in the negative 2 just to see what the y value is. Pretty sure that's what it is, right? Because it'd be 8 minus 26. Yeah, it'd be negative 18. And so this thing factors. We said the two numbers that multiply to be negative 5 that add to be 4 will be negative 1 and positive 4. 5. Thank you. Come on, active panel, catch up with me. Oh, look, active's going to crash now. Yay! All right, cool. Now we're good. We're good. It came back. So our x-intercepts are at positive 1 and negative 5. I know I wrote them backwards, but whatever. Hence, sketch the graph. We know where it crosses the x-axis, we know where it crosses the y-axis, and we have the vertex. Way more than enough information to sketch this graph. But we know we have big, big, big negative numbers on the y-axis. So we're trying to go all the way down to negative 18, right? And we have to deal with negative 10. So how about we go by 2's? Negative 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, so I went by 2's on the y-axis. And x's, we'll just go by 1. Oh, crud. My graph is, I've extended it to the right instead of to the left. No, that's because that's what I did, right? All right, well, I'm going to cheat. Because I can do that. Magic. Ta-da. We're just going to scoot that. There we go. Sorry about that. So what do we got? Negative 5, go by 1's. So there's positive 1, and here's negative 5. 1, 2, 3, 4, 5. 5. All right, negative 5. Y-intercept, or x-intercept, x-intercept, y-intercept, and vertex at negative 2, comma negative 18, way down here. There we go. Good enough. He's back. I can see him. Easy peasy lemon squeezy. We good? Nobody's panicked about graphing quadratics yet? Alrighty. Let's see what we got next. So we've pretty much already talked about this, but we're going to learn some more vocabulary terms here in just a second. We've already talked about the fact that when your discriminant is negative, which is what you're seeing here, you have a quadratic that never touches the x-axis. When your discriminant equals 0, like you have here, you have a quadratic who's just touching the x-axis, not cutting through it, just sitting on it. Vertex on the x-axis. And if your discriminant is positive, then you're cutting the x-axis twice, which is what the IB people like to say. It means you're going through it twice, okay? We've already done that. We did that stuff Friday, right? But how does it relate to more vocabulary that I didn't even know until I started teaching this course? I'm just refilling in this box. We have some more information to write here in the box below regarding the discriminant. Really neat stuff. So if the discriminant is negative, then we know that we have no real roots, right? This is no real roots, which basically means doesn't touch x-axis. If the discriminant is 0, we've already talked about this a couple times, we have one repeated root. And this puts the vertex on the x-axis. And then if your discriminant is positive, you have two distinct real roots. Well, I'm not going to write real. Board is struggling. Two distinct roots. And this crosses x twice. So two terms that I learned from our textbook, and it's not just me. I went and asked a couple of the other math teachers, and they're like, no, I've never heard of those terms before. They must be taught in other countries. Are positive definite and negative definite. And then they give you a picture for it. So a positive definite quadratic looks like this over here. It's a quadratic that points up and never crosses the x-axis, right? It's positive definite, meaning all of its values are positive, all of them. Because, 0 is not positive. 0 is just 0. So positive definite means, yeah, every single y value this thing has is a positive number. Well, to see if a quadratic is positive definite without having to graph it, you would just look at the a value and the discriminant. So a quadratic is positive definite if and only if your a value is positive, because that would have it point up, and this has to also be happening, the discriminant is negative. Because a negative discriminant means no real roots. So we have a smiley face with no real roots. Positive definite. And negative definite is a graph for whom all of their y values are negative. Never touches the x-axis, because that would be a y value of 0. And remember, 0 is not positive or negative. So we have every single y value is negative. That happens if and only if the front number is negative, and, because negative makes it point down, and the discriminant is also negative. So, just tells you the relationship that the graph has with the x-axis. And this is the kind of stuff I'm talking about when I say a deep understanding of material. Could a student graph? Sure. But could they tell me something about the graph, a lot of stuff about the graph, without graphing it? That's what we're wondering. And then we just have one more page and section 1.2 is behind us. Questions, comments, or concerns before we get to the last little bit? No? Crickets. Gotcha. Okay. Anybody panic if I move? No. One person. All right. There we go. Use the discriminant to determine the relationship between the graph of each function and the x-axis. Great. Well, you know what? I can already tell you that this graph points up. I could see that my a value is positive. So we know this graph points up. Now what we need to do is figure out what's going on with the discriminant. B squared minus 4ac gives me 3 squared minus 4, a is 1, and c is 4 again. So that 9 minus 16, which is negative 7. So I have a discriminant that's negative. I have a positive front number, and I have a negative discriminant. That graph looks like this. So this is a positive definite quadratic. I don't want to write all of those words. I'm sorry? Well, you probably did discriminant stuff in previous classes, but the words positive definite and negative definite, I couldn't imagine. Like I said, I've never seen them in any American textbook. It must be something that's done elsewhere in the world. But this is all about international mindedness, right? Math is probably the hardest one to have international mindedness in because math is a universal language. Like, that means that the IB math in China is the same IB math that you're doing here. We all speak the same math language. No, they don't. No. The word 2 in Chinese is different than the English word 2, but the symbol for 2 is still a 2. No, they wouldn't use a Chinese character. No, math is math. If they write the word, it's different. No. They use the same number symbols as everybody does. Our number system is Arabic. Anyway, let's do it again. We know that this graph points down. We know that. This graph points down because the front number is negative. So now we just need to figure out what's going on with our b squared minus 4ac. So 5 squared minus 4ac. Is that 25 plus 8? Or 33? Oh, so I have a positive discriminant. So I have a positive discriminant. That tells me I have 2 real roots, 2 distinct real roots. The 33. I just forgot to write the other 3. Sorry. This math is not true. So there you go. So the discriminant is positive, front number is negative. This graph crosses through the x-axis twice. So we have 2 distinct real roots. So it's like it cuts the x-axis twice. That's what they want you to say. But same idea. We basically already did this. Now I just added positive definite and negative definite as options for you. Is that a question? Nope, he was stretching. Okay. And again, we've already basically done this. It's the discriminant stuff from Friday. But here it is again. Came up in the book more than once. How about that? I wonder if it's important. It says find the values for k for which that quadratic cuts the x-axis, touches the x-axis, or misses it completely. So this cuts the x-axis. This is going to be discriminant is positive. This touches the x-axis. This is going to be discriminant is 0, and the misses is going to be discriminant is negative. It's like that. Well, this discriminant is actually pretty easy to find. B squared minus 4AC, that gives me negative 6 squared minus 4 times 1 times K. So this is just 36 minus 4K. Where does it equal 0? Well, yeah, but I mean, like, what does K have to be in order for the discriminant to be 0? 9. Yeah. We only have one critical value. So we might as well practice our sign diagram stuff, right? There we go. 9. It only has 2 zones. Let's check to the left of 9. Let's plug in 0. 36 minus 4 times 0. Yeah, that's positive. And let's plug in a number like 10. 36 minus 40. That's negative. So for A, it cuts the x-axis on the interval from negative infinity up to 9, not including. For B, touches the x-axis at K equals 9. Remember, it's K, not X. Please don't say X equals 9, it's K. And misses completely when you're talking about negative K values, or negative Y values, excuse me. So that's when K is greater than 9, so from 9 to infinity. And I believe that's it for the notes, correct? Pretty cool.